Hi everyone, I'm Jose Miguel Orcas from the University of Malaga. I'm going to present the work entitled Extensible and Modular Abstract Syntax for Feature Modeling based on Language Construct. Since the definition of the feature models 30 years ago, numerous language constructs have emerged. From the basis construct defining fora, more advanced modeling concepts have appeared to model complex requirements of different domains. For example, non-Boolean feature models to support numerical features, features with cardinalities, features with attributes, compositional features, and complex constraint. Each of these language constructs usually comes with his own syntax and semantics, and often coincides with the definition of a completely new modeling language or a new tool to support it. Despite the successful of feature models to specify variability, no standard has emerged. Nowadays, the software product community is interested in the definition of a single common variability modeling language. In fact, in the last 2 years, several works have been published pointing to the definition of such unified language. This work covers multiple topics, such as best practice for feature modeling, constraint modeling, language level for feature notations, a unified intermediate language for variability, reviews about variability modeling language, reviews about practical tools, or systematic studies about automatic analysis, or even tertiary studies about variability. Despite all of this work, why is there not a common language at this point? The problem of defining a common language is the existing trade-off between the expressiveness of the language to satisfy requirements in different domains and the effort of building tools to support all language constructs. The same trade-off exists for the analysis capability of the language and the performance of the solvers. Several informal classifications have been proposed to classify the language construct based on their expressiveness. Everybody knows what we refer when we talk about basic variability modeling. I mean the basis construct that are often supported by all tools. But when the complexity of the requirement increases and more advanced language constructs are needed, it's not clear in the community the level of expressiveness, what language construct each level should support, or the nomenclature of the different level. Anyway, they agree on the use of modular and extensible language design and the use of language level to support a feature modeling language. The main objective of this work is the definition of feature modeling language with different level of expressiveness, following an extensible and modular design, and based on the language construct of existing language. So our research questions are the following. How can the extensible and modular design principle be applied to feature modeling? What specific language construct should be considered in a feature modeling language? So what is our proposal to achieve this objective and to answer to these two research questions? The key idea of our approach is modeling the different language constructs in separated metamodels, which allow a practitioner to choose only those language constructs that he or she needs for a practical use. The perfect scenario will be to have a common abstract syntax for all possible language constructs and generate a specific subset to cover the special need of practitioner. In the following, we are going to briefly present the formalization of our approach, an instantiation with the existing language construct, and an implementation. Any modeling language consists of three elements: a syntactic domain, a semantic domain, and a semantic function. In feature modeling, the syntactic domain corresponds with the set of all feature models that can be specified with a given abstract syntax that we will see in the next slide. The semantic of a feature model is his set of valid products or software product line. and thus the semantic domain is the set of all existing software product lines. The semantic function maps a feature model with his software product line. In this paper, we focus on the syntactic domain, which corresponds with the abstract syntax. While the concrete syntax is the physical representation of the feature model in terms of textual notation or diagrams, the abstract syntax is a representation of the feature model which is independent from his physical representation. The problem of current language is that they have different concrete syntaxes and different abstract syntaxes, complicating their interoperability. One way of specifying the abstract syntax of a feature modeling language is using metamodels. So here we use the metamodel to define the abstract syntax of the language construct for feature models. But what is exactly a language construct? We define a language construct as the abstract syntax of a specific variability modeling concept, such as feature, root, optional feature, numerical feature, and so on. We also define a special language construct to model the concept of a feature model as a container of other modeling concepts. For example, the feature model construct includes what we understand as a basic feature model, the attribute feature model to define feature model with attributes, or the numerical feature model to support non-Boolean features. Finally, we define an initial metamodel with at least the basic feature model construct, and any other feature model should extend this construct. And then, with these definitions, our approach consists in a set of interrelated metamodels. Each metamodel defines a non-empty set of different language constructs. In addition, we define three relations: the extension of a language construct to specialize an existing language construct, the composition of language constructs to define constructs using other language constructs, and a dependency between metamodels. Metamodels depend on another metamodel if there is a language construct that uses another language construct defined in that other metamodel. By using one of these two relationships between language construct, I mean the extension or the composition. We present an instantiation of our approach where we use more than 50 language constructs taken from existing feature modeling language from the literature. Despite the high number of metamodels and language constructs, the modular design of our approach allows practitioners to use just the parts they are interested in. We classify the language construct in 4 dimensions, proposed in this paper as follows. Configurable elements, where we group the language construct based on the type of variability they model. For example, metamodel 0 contains the FODA concept, metamodel 2 to 5 different types of feature groups, metamodel 6 to 7 parent-child relationships, metamodel 8 to 10 non-Boolean feature, and so on. The next group of language construct are to support constraint. So we separated the modeling of the constraint based on their expressiveness from basis constraint to propositional logic, first order logic, relational and arithmetic expression, and so on. The next group is related to advanced construct, focus on the scalability to handle big feature models such as compositional operators, import, includes. These constructs are usually orthogonal and do not influence directly the semantic of the feature model. Finally, we also consider the language constructs to work with configuration of the feature model, like a partial configuration or full configurations. Let's see the implementation. We implement our approach using Core metamodels. We choose the Eclipse modeling framework because it's a well-known and stable model-driven framework, providing good support for model transformation, code generation, serialization, models and runtime. and also because directly implement all concepts that we use in our approach to define the language construct, such as classes, attributes, and relations. The feature model construct is always implemented as a class because it serves as a container of features and constraints. The rest of language construct can be implemented as a class, an attribute, or a relationship. This is an implementation decision of its abstract syntax, but that is independent from the semantic meaning of the language construct. For example, the feature construct is implemented as a class. The root feature is a composition relation. The optional or mandatory feature is a Boolean attribute. The parent-child relationship between the feature is a composition relationship between two features. The groups, alternative, or group are implemented as classes. And finally, the cross-tree constraint are implemented as an abstract class in this initial meta model in order to allow specifying concurrent constraint in separated meta model. Following these principles, we can implement in separate meta models more advanced language construct, for example, the non-Boolean feature models, numerical features, or as we say, implementing different kind of constraint in independent meta models. The conclusion are that our approach advocates for a modular and extensible design that allows practitioners to decide which language level support based on their needs. Using just the needed language constructs may lead to better performance and analysis capabilities that are not available for a full language with all possible constructs. As future work, we are working on the basis of our approach to take the advantages of the model-driven engineering techniques to provide support for several activities. For example, to provide interoperability between language, tools, and solver with different expressiveness, to analyze the formal properties of the language based on their language construct, facilitating the evolution of feature models, and improving the benchmarking with the feature models.